Okay, in this particular video, what I want to do is I want to take a look at the problem that we discussed last Tuesday. And that problem was the situation where we had a cogeneration. In this particular case, let's go back to a Blackboard. And I'll just remind you of that particular problem. It's in the week 4 videos. Down here, it's key problem OUY. And I passed out in the class yesterday or on Tuesday. I passed out the statement of this particular problem. This particular problem had 2 stages of turbine expansion. Both of the stages of turbine expansion were 80% isentropic efficiency, and so we have to make sure that we know how to handle the isentropic efficiency, and therefore we identified a state 2 and a state 4 as being the isentropic condition, where state 3 and state 5 corresponds to the non-isentropic or actual condition. And then the other thing that we had to do, once we allowed the full amount of the fluid to come in, and that was 1 kilogram per second, we then had to split the state at 3 to go over to the process heater and to go over to the low pressure turbine. And so we opened up, or we recommended that you develop a state 13 corresponding to the 0.3 kilogram per second of fluid that came over to the process heater, and a state 23 that was the remaining 0.7 that went over into the low pressure turbine. And so by splitting them in that fashion, we could then look at the high pressure turbine and the low pressure turbine with the corresponding energies coming in and going out. We then had, coming back from the process heater at a little bit lower pressure and at a given temperature, we were able to establish state 8. And then state 8 trapped to the lower pressure of the condenser in an isenthalpic device. And then the condenser is what brought all of the fluid back together, all of the 5 fluid and all of the 9 fluid, so that we had 1 unit or 1 kilogram per second going to the pump, and the pump taking it all the way back up to the pressure of P1. And so with that in mind, what I'm going to do in this particular problem is I have already solved the problem. I have it in a document, in a Word document, and for expediency here today, what I'm going to do is I'm going to open up that document, and I'm going to copy and paste the solution into the test software and kind of speed some things up here. So let me go to my downloads, and that's where I have the problem. And so I'm going to open this Word problem up. And like I said, I had already saved the solution, the states, as well as the devices, as well as some calculations with some user code. And so I'm going to copy that. I'm going to put that away. I'm now going to go back to my original. I'm going to go to my test. I'm going to go into the test app that corresponds to the vapor power system utilizing a phase change fluid. I go into the app. I go to the I/O panel, and I paste in the information, which was the states, the device panels, as well as some user code, and I'm going to load. And so what this does then is take everything that I did before and load it into the test software. So let's just go and review what I did then. So At state 1, we have the pressure and the temperature coming into the turbine with a mass flow rate equal to 1. State 2 is the isentropic expansion, and there's the entropy to 0.2 megapascals with the full m dot, and so that's the first stage of the turbine. State 3 then was the real condition at the same pressure, at pressure 2, at the same m dot, but now my enthalpy is the real enthalpy. It's no longer the isentropic process, but rather it is H1 minus the isentropic work times 0.8. And so that's my real state 3. And then, as I said before, let me go ahead. I then identified a state 13, and state 13 has the same pressure and the same enthalpy as state 3, but it's only 0.3 kilograms per second. Likewise, I went ahead and generated a state 23. Same pressure, same enthalpy, but then the remaining amount of m dot. So there's the 0.7. So this then goes through the low pressure turbine. And so now we're ready to take a look. So as it went through that process, state 4 now is at the low pressure. It expands to 6 kPa. The m dot is m dot 23, which is the 0.7, and the value of entropy is equal to the entropy at state S23. Okay, that is the entropy coming in at that state that we just defined. And so this is the state 4 is the isentropic work of the low pressure turbine. I then go to state 5, which is at the same pressure. And now you see that the enthalpy is the starting enthalpy, which is H23, minus then the isentropic enthalpy times 0.8. And so that's the isentropic work. We only develop 80% of that. We subtract that from the incoming enthalpy. And so that's how we identify the enthalpy at state 4. Again, state 5 has the m dot associated with that particular condition. And now we can go to the rest of the states. State 6 then is the fluid, the full fluid coming through the condenser, and the condenser has an output quality of 0, and it's at pressure 4, and so this is our state 6. State 7 is going through the pump, and we know that the pump is taking the fluid back up to the high pressure, and it's doing it in an isentropic fashion, and it's the full mass flow rate. State 8 was what came back from the campus heating system, and so it came back as described with a lower pressure. Instead of 0.2 megapascals, it comes back at 0.1 and at a temperature that's known of 60 Celsius. And so that's the condition coming back at state 8, and it has an m dot equal to m dot 13, which was the 0.3 kilogram per second split. State 9 then is through the expansion valve, through the trap, and we know that it's going to the pressure of the condenser, which is 6 kPa, and it's an isenthalpic device. No change in enthalpy, and the flow rate is the m dot 13. And so now we have 9 that's going to go into the condenser, as well as 5, which is going into the condenser coming out of the low pressure turbine, and that's all forming to become 6, which is the output of the condenser. So now we've got all the states identified, and so now it's time to go and take a look at the device panels. Okay, now this is where things are a little bit different. This is a multi-mixing device panel that represents the two stages of the turbine. Looking at the two stages of the turbine, in essence, what you have coming in is the full mass flow coming in at state 1. Coming out is the amount of mass that, excuse me, that left to go over to the campus. Okay, and so that's coming out. And then we have the remaining mass, which is state 5, that went through the rest of the turbine. And so by looking at the turbine as a single inlet and a 2 outlet, we can then say that the Q dot is equal to 1 and the total power generated by this adiabatic turbine is 668 or 686 kilowatts. So we could have done the exact same thing, but just added 2 stages of turbine. One stage would have been a portion. We would, things get a little complicated because we have to maintain the mass balance. And so the question would be, we would need to generate a new state that represents 1, but only part of the fluid. So we would have to generate a new state, maybe call it 11, which was 0.3, and another state, maybe call it 21, that was 0.7. So we could then have those coming in and going out, giving rise to power. But by having the capability of doing a multi-mixing device, we can handle both stages of the turbine in this fashion. Our mass flow is conserved. Our energy balance is then used in order to determine the amount of work generated for the total system. Our second device then is from 13 to 8. Now what this device is this is going over to the campus system. And basically we have the 0.3 kilograms per second going over and coming out or coming back at state 8. And what we see happening for that enthalpy change is that the heat release is 719. Okay, so now it's negative because it's left the steam, but it actually is 719 that was actually delivered as a deliverable for the campus, for the power plant. And then we have device 3, which is now that, that condenser. And the condenser has state 5 coming in from the second stage of the turbine expansion, state 9 coming in from the expansion valve coming from the campus system, and then it all comes out at state 6. And so it's a multi-mixing where we have, this is the 0.7 and this is the 0.3 kilograms per second, and it all forms to come out as 1 kilogram per second mass flow. And so the enthalpy balance is performed because we know all of the properties. The work is being done is 0, and so we see that we're rejecting about 1,500 kilowatts of heat from that device. And then we also have device 4, which is the pump. The pump takes the fluid from state 6 to state 7. No heat transfer, a very little amount of work, only 2.5 kilowatts of work required for the pump. And then our final device is the boiler, and the boiler is taking the full fluid flow rate at 7 and bringing it up to state 1, which is delivered to the first stage of the turbine. And with no work being done in the boiler, we see 2,901 kilowatts of heat going in. And so those are the device panels. If I went to the cycle panel, one could see that they're all identified here. Okay, here was the heat that was going in the boiler. This term right here you have to be careful with this one because this includes both the condenser as well as the heat that was delivered to the campus heating system. And then we have the work of the two turbines together, and then the small amount of work due to the pump. And so one has to be careful with this thermal efficiency because this thermal efficiency is, as defined, it's this net work divided by this heat transfer in. And so it's a relatively low number, okay? And it's because we sacrificed a lot of the energy from the turbine, bringing out 0.3 kilograms per second and having it heat the campus. And so there is some of this that needs to be added to the net work as the numerator of the thermal efficiency. And so since this panel can't do it, in the I/O panel, I went ahead and had the I/O panel print out for us the pertinent pieces of information. And so what it prints out then is, I asked for the work. This is the exterior work associated with the turbine, and that was the 860 or 686. And then we also had the work of the pump, and we see that that's a minus 2.5. I also printed out this Q.2 was what we sent to the campus. Okay. And I also printed out Q.5, which was what the boiler supplied. And so the numerator in our thermal efficiency equation then is the positive turbine work, and then I subtract the negative pump work. I then subtract the negative campus heating. And so I want this to be a positive. And so all in total, we are actually delivering 1403 of goodies. Okay. What is that? 1403 really is 686 minus 2.5. And so it's about 684 units of work that could maybe be converted into electricity, but we also were able to get 719 units of heat from that heat that we actually brought into the system at the boiler. So the denominator then is just the boiler heat, and that was the 2901. So then when I take the numerator divided by the denominator, we have then the efficiency of this cogeneration plant. And so what one then sees is almost a 50% efficiency associated with this vapor power plant. And so basically that's telling us that for every 2 units of heat that we deliver to the boiler, we're able to generate or deliver heat or power, work, electricity out of that. So that's a fairly good return on our investment. So that's the solution to this problem, OUY. I did it this way in order to kind of speed it up a little bit, but I wanted to show you that with a little bit of selective numbering. And again, after reading the problem and recognizing how you are going to put things into the various device panels, you can then set up all your states, generate all of your device panels, and then take a look at the output and move from there. So that's the end of that.